My watch says 1:30. I'll wait for one more minute, and then we'll start. Actually, I want to go to the other screen first. Stay here for a minute, and then... Okay, good afternoon. My name is Burak Ekşioğlu. I'm an associate professor in industrial and systems engineering at Mississippi State University. I am also the director of one of the tier 1 UTCs that was selected in 2012, the National Center for Intermodal Transportation for Economic Competitiveness. I will be moderating the session this afternoon. We have 6 speakers, as you can see in the program, and all 6 of them are here. What I'd like to do is I would actually like to introduce all of them up front, and then to save some time between transitions. So what I'll do is for the speakers, about 15 minutes into your presentation, I'll be sitting here, I'll signal you, indicating that you have about 3 more minutes. And then when you have about 1 minute left, I will actually stand up and start walking towards you. So that also is a sign for the next speaker to start walking towards the podium. And as that speaker answers questions, we'll pull up the presentation for the other speaker. So you have 20 minutes, which includes questions and answers. Our first speaker today is Adel Elfayoumy from University of Alabama, Birmingham, standing right up here. Our second speaker is Frank Southworth from Georgia Tech. Our third speaker, Bahareh Inaloo from Florida International University. Fourth speaker, Danny Boston from Georgia Tech. Fifth speaker, Sarah Smith, Georgia Tech again. And last speaker, David Lee, from Georgia Tech. So with that, I'll turn it over to Adel. One other thing, we have 2 microphones. If you prefer to hold one and speak into this, I think this is easier, but we have the other one also.
Thank you so much. Hi everybody. My name is Adel. I'm a PhD candidate at University of Alabama at Birmingham. Our topic today is about the use of heavy vehicle in case if we double to meet any future increase in the freight demand. The use of heavy vehicle is very important for any economic success. For the time being, it's expected to be doubled in the next 10 years, and this increase must be accommodated either by increasing the number of trucks or increasing the truck weight itself. Both conditions affecting the truck, affecting the bridge, adversely affecting the bridge. Under the current conditions, freight conditions, 40% of US bridges is classified as structurally deficient or functionally obsolete. In case we double the number of trucks or double the weight of the truck itself, will affect the bridge in so many ways. One of them, we increase the congestion over the route, over the bridges. Number 2, repetitive load might cause some fatigue problems that affecting the bridge service life. The third one is increasing the weight of the truck is actually affecting the load effect over the bridge. The main one of them is the bridge cost. Increasing the traffic over the bridge will increase the cost due to the accelerated retrofitting and the maintenance operation over the bridge. So in our study, in our research, we'll study the impact of meeting the freight demand in future over the service life of the bridge and the associated cost in terms of fatigue and load effect. To achieve these goals, we have 5 tasks. The task number 1 is to characterize the traffic measured over the bridge to detect the extreme gross vehicle weight of a certain period, return period. Number 2 is to determine the characteristic of the bridge population under the effect of load and fatigue. Number 3 is to submit a new technique using FE model to simulate the stressed and unstressed bridges using ANSYS FE model. And number 4, to study the impact of increasing the traffic and traffic load on the service life of the bridge. And number 5 is to study the impact on the bridge cost. In number 1, using the WIM data, we can classify the trucks in terms of number of axles. As shown in this table, we have certain data and we classify it as per the number of axles, and we could build the histogram to detect the most prevalent trucks. And we can see that the 2 axles and 5 axles truck is the most prevalent truck. Out of these trucks, we'll consider only the 5 axles because of its weight. And using the extreme value theory, we could detect the most expected extreme gross vehicle weight depending on 2 scenarios. The first scenario dealing with the gross vehicle weight of the truck observed daily. We could detect, we built a MATLAB program to calculate the 1,000 year truck. The extreme truck could be expected in 1,000 years. The second scenario we're dealing with is based on the axle weight itself. The first one was dealing with the gross vehicle weight, and second was dealing with the axle weight itself. Accordingly, we could calculate the gross vehicle weight. In both scenarios, we kept the spacing between the axles as the same as the ASHTO legal truck because of the low standard deviation of the observed data. And fortunately, we have almost the same weight in both scenarios. In first scenario, we have 167 cab truck, and second scenario, we have 170 cab truck. And by this trucks, we achieve the goal of first test. In second test, we test different scenarios of bridges to study the impact of increasing the load and the fatigue of the trucks. We have steel bridges, pre-stressed bridge, different span starting from 30 up to 140 feet length bridge, using different programs, CSI bridge and the VERTS bridge. VERTS is developed by ASHTO, and we are using numerous number of trucks, starting from the ASHTO design trucks, HL93, and the 160 and the 171 we got before, and the 97 TRB and 97S and 3S2 truck. One more related for the fatigue, we could get an 85 cab truck. Out of the 5 axles truck, we build a histogram to get the most frequent truck, which in our case is 85 cab truck, and run numerous of bridge scenarios for this truck and other trucks, and we got this graph. We can see for a steel bridge, the black one represents the capacity of the bridge, and the red is for the VERTS, and the blue is for CSI. We could see all of bridges are safe, subject to it's safe for HL93. We could see the HL93 almost touching the capacity curve at all points. Afterward, by the way, the HL93 is 70 cab truck only, and we have 170 and 167 and 85, which is more than 87, almost a double. And we save for load effect. Even for the fatigue, because of the 85, the most frequent truck, we're safe too. The same happened in the pre-stressed. We can see that the black line referring for the capacity, and other lines referring for the CSI and VERTS. And by the way, VERTS is very close to the capacity of the bridge, more than the CSI bridge program. So we could get the bridge population in different construction material and different spans. Now we are shifting the window to the future, increasing the number of trucks and increasing the weight of the trucks may cause some accelerated maintenance required for bridges. And to simulate it, we need long-term performance of bridges and maintenance material. We have a lack of information about the resin material that is used in the FRB technique, strengthening technique. And to get this crucial information, we asked the University of Auburn for help, and they provide us with the master graph of the models of elasticity of the resin material that's shown up there. And we can see in 100 years, we have less than 1% change in the model of elasticity of the resin material. And this is the model we built using the ANSYS, separating the deck, girder, resin material, and FRB using different elements in ANSYS. And this is the configuration of 3 types of bridges, 60 feet long and 118 and 140 long. And this is the outputs of the ANSYS. This at the time of construction, no loading. And this after 30 years where we are expecting the fatigue problem due to the cyclic load and due to the losses of pre-stressing. And afterwards, we intervention with the FRB strengthening. That's shown here at the time of 0 time of FRB. These are stresses in the girder, stresses in the resin material, stresses in the FRB element itself. We got this graph. We'll deal it with. Here is the graph. We are comparing the time versus the concrete bottom fiber tensile stresses. In case of the current traffic, we have this graph. We can see these are changes of the stresses due to the decay of the pre-stressing stresses and long-term losses. And at this time, at 30 years, we need the intervention of FRB strengthening. And we can see the sudden and immediate improvement in the performance due to the adding the FRB. Afterwards, we simulate another scenario, doubling the number of trucks. Here is the effect of doubling the number of trucks. We could see that the fatigue problem could happen much earlier, midway of the 30 or around 15 years. And the other scenario, to meet the increase in freight demand, we are increasing or doubling the weight of the truck itself. We could see that the stresses has been doubled, and after 30 years also, we have intervention of FRB, and we can see the immediate improvement in performance of the concrete. We do the same for 60, 118, and 140 feet long bridge using different trucks. We have HL93 H2 fatigue truck and our site-specific fatigue truck, which is 85 kp truck. We do all of this because of the limited budget of maintenance, so we could maximize the effectiveness of this budget, and we have a futuristic plan for the bridge. In test number 4, we are studying the impact of meeting the increase in freight demand on the service life of the bridge. We are studying the key factors of 2 equations, considering that one of the common bridges in US, which is a steel bridge with a concrete deck. We have an equation for steel elements, and we have an equation for concrete deck. It's important for what? We could see this our graph we got from the last task. It could help in this way. We have 2 scenarios. One scenario that we have the bridge service life comes before this time, like this, and this time we need to intervene with FRB strengthening. And the other scenario that the bridge service life comes after the intervention, so we are safe. In test number 5, this is the overall of the whole story. We are studying the impact of meeting of freight demand, increasing freight demand, on the cost of the bridge. The cost of the bridge consists of the construction cost and the maintenance and retrofitting cost. maintenance depending on the technique, the method. So it's a money. And in this case, we could see that the performance could be right here, or right there, or right there, depending on the cost spent in the maintenance and the technique and the approach used in maintenance. And so we are providing a management tool for the bridge managers to have a future plan for any necessary maintenance that covers the whole life of the bridge. As a summary, we are developing a method to characterize the representative vehicle over a certain period of interest. In our case, it was 1,000 years. Number two is to characterize the bridge population depending on the load effect and fatigue. Number three, we are providing a finite element tool simulating the technique of strengthening intervention based on deficiency problem identified previous. Number four, we are investigating the impact of meeting of the increase in freight demand on the bridge service life. And number five, we are providing a comprehensive tool for manager to have a head plan necessary for intervention during the long term of the bridge and covering the whole cycle life of the bridge. I'm happy to have questions if you have.
We have actually plenty of time for questions.
One question I had was, you said 1,000 years
Yes.
worth of data?
No. We are detecting 1,000-year truck. That the worst case this is the worst truck we might have in 1,000 years. This by actual seismic code. So we use this value as a return value for the truck. This is the most expected based on our site-specific data. This is the most expected extreme gross vehicle weight in 1,000 years.
Any other questions? All right, thanks, Adel.
Thank you so much.
Okay, our next speaker is Frank Southworth from Georgia Tech.
Good afternoon, welcome to Atlanta. You can tell I'm a native by my accent. I'm a principal research scientist here at Georgia Tech. And my co-author is Denny Smith, who's sitting over here, who's a PhD student here at Tech. And what I'm going to talk about is a project that's only recently got going. We've already made a bit of headway. And we're interested in estimating the commodities, understanding what commodities move on our major highways. Now, this was initiated in part by MAP 21, which is, you know, the legislation. If you're working in freight, we're supposed to help, the DOTs are supposed to develop performance measures and performance targets for their freight systems, and they're currently designing at the federal, the state levels, strategic freight corridors. So we're taking a look at freight corridors, and one of the things you ask yourself, first of all, is, well, what freight's on the corridor? Well, we actually don't really know. And one of the reasons we don't know is that we have a very hard time getting enough data to actually represent the commodity flows. So this project's looking at how to estimate commodity flows in sufficient spatial and industrial sector detail so that we can put them on the network, translate them into truck movements, of course, and then calculate what kind of flows are going on. So we've got a lot of truck counts, we're pretty good at estimating truck flows, but we really don't know what's in them. And the final motivation for the project is also to look at what is the value of time savings for congestion. We heard earlier from the commissioner about let's be more efficient in how we invest our assets. Well, if you don't know what the cost of congestion is, it's pretty difficult for you to really effectively assess which roads, which parts of roads, or how to improve your infrastructure, because we don't have a very good measure. And we know the value of time is a very significant, often the most significant component of the value of the monetary benefits of improving developing highways. So we're taking a look at that, and we break this down into three questions. What goods are actually moving over the corridors now and in the future? How fast are they moving? And what do these delays actually cost us in dollar terms? And us, it's the economy, it's ultimately the consumer. So the objective specifically was to develop improved measures of value time savings for different classes of trucks using a method that can be applied to intercity corridors. And so the tasks in here are pretty simple. Define a study corridor, generate a matrix of origin, destination by commodity, by truck class flows based on the location of specific freight generating activity. Carry out a multi-class, and we're going to use an origin-based, and I'll say why in a minute, congestion-sensitive assignment of trucks to the selected corridor. We're going to use the latest approach to traffic assignment, which is theoretically consistent with tracing back from a set of truck counts and truck flows to the origin, destination, and commodity which generate those flows. Now, if you're in the transportation planning business, we have a lot of traffic assignment models which optimize the flow on minimizing the transportation costs by estimating the most likely, the optimum allocation to link points, to link volumes. Well, that's fine, but you can't back engineer it to the origins and destinations by commodity. You really do not do that, because we've made an efficient method for estimating link volumes, but you need a path-based model to do it. You also need more than that. You need to know where they start, where they end, and in our case, what commodities are moving. Why does it matter what commodities are moving? The literature on commodity value of time varies from $10 an hour to $200 an hour. So if you're going to make the value, the average, for example, the ATRI, which is based work out of here in Atlanta, the American Transportation Research Institute, estimates it's around $68 an hour on average for truck movement. But the range is tremendous. Well, if you're going to do economic benefits, you want to know if it's $20 an hour you're saving or $200 an hour. And we're trying to get back to a number that will be reasonably representative. Some corridors will be very high because of the type of commodities. And so the final task then is to estimate this dollar value using the latest developments in value of time, including value of time reliability. Oh, and then we have to write a report. Okay, so the challenge then is to overcome this data limitation, which we're all faced with. And the innovation then is to look at different ways to disaggregate it, use the latest in assignment modeling and in value of time modeling. Okay, so progress to date. The first thing is define a corridor. Well, we decided we're in the southeast, we're in Georgia, so we're going to take a look at the corridor here. And what we do is we're breaking down the flows. So all those little blue dots are the freight analysis framework. The data we have right now is 121 internal regions within the US and 8 foreign regions. And that's the level of spatial detail for which we actually have observed data on commodity flows. That is, reasonably, it's not entirely observed, but it's a pretty good sample. And we have to break it down. If we want to put flows in, then every state or MPO has to break it down. So we break it down, we take it down to the counties in the 6 state regions surrounding Georgia. And as you see, we're going to take it down even further to the zip code level, and in some cases, we're going to try to take it down to the individual, what we call special freight traffic generators, where we know there's a lot of traffic going on. And one of our tasks is to try to figure out how good is the data that's available for doing this. There's been quite a few attempts to do it, but how good are they? So here's an example of a corridor. Now, we thought we might try I-85, but then we decided we'll do I-20, starting through Atlanta and going up to Greenville. So the first round dot is Huntsville, Atlanta, Greenville. One of the reasons for doing that is we have freight analysis framework flow data by 43 commodities between those 3 metropolitan areas. So we have a basis for adjusting our eventual estimates back to the quote-unquote government number, or best government number they can get for the amount of commodities moving. So we're going to take a look at that. So we've chosen our corridor. And then we started to look at how will we disaggregate flows from broad regions like Atlanta, Huntsville, the rest of Alabama, the rest of Georgia, In Georgia, we have Atlanta, Savannah, and the rest of Georgia. Well, that obviously isn't much use for estimating flow models other than at a national level. So we're breaking it down, and I put it up here. I recently completed a review for Oak Ridge National Laboratory, which is in turn done for the folks who are developing the new FAF of federal highways. I'm one of the, I shouldn't admit to this, but I'm one of the principal developers of the FAF, so I know what's wrong with it as well as what's right with it. And we found that there are quite a lot of it, 30 or so papers in the last few years that look at how you break these flows down from very broad regional numbers to county or below. And you can do a simple proportional weighting, take the flows going into or out of, say, Atlanta or FAF, a broader FAF region, and just weight by employment. A lot of studies weight by employment in the county to distribute the flow to the counties. Weight by population is the attraction. It doesn't work in most commodity cases. In a 1 or 2, it might be okay. Regression models have been developed, but they use the 123 points of the FAF data. So as soon as you start disaggregating to a different spatial level, I have a PhD in quantitative geography, and anytime you change the zoning system, first thing we tell you is you're going to change the results. So we have to deal with that. That's the best we have right now. We've also been looking at input-output models, where we try to build up information given the different industries. We can get down to NAICS, North American Industrial Classification System, 6-digit codes. The data's pretty bad. Most people use 3 digits. And we try to aggregate those up from the county level and use them to estimate truck productions, attractions, and eventually truck flows. There's some interesting simultaneous equations modeling going on out in California and elsewhere, direct demand models which try to estimate production, consumption, and the flows, the cost of the flows simultaneously, which may work for freight. It doesn't work very well for passengers. Once you've got an estimate of the productions and attractions, the O's and D's, you have to find some way to distribute the flows. Most people use a spatial interaction model, gravity model, entropy model. Some people just do a simple biproportional mix. So if you've got an origin zone and a destination zone, you've got 20 counters in the origin and 30 in the destination, you've got a 20 by 30 flow. It doesn't work very well if you're in adjacent zones. It may work for very long distance zones. So we have to go through the process, trip generation to distribution. Then we have to do some conversions to trucks to passenger car equivalents. We talked earlier today about passenger car equivalent estimation. We have to find a way to include empty trucks, and there's quite a bit of literature on that. And then eventually assign this to the highways using a multi-class assignment, and we've chosen an origin constrained multi-class assignment to get the flows onto the network. Now, these are various steps that we have to go through, and we thought rather than try to do each step very carefully, we'll have to go right through first of all and see what we can get. We're using Califor's Transcab software mostly. No, I can miss this one. That's the detail in the freight analysis framework. Basically, every state that disaggregates flows for freight starts with the regions over there, 123 regions, 43, really 42 commodity classes, and the 7 models, and we're focusing on truck. So that's where you start at when you're breaking it down, or at least that's what you try to fit it to. So in the top left corner, I'm not going to go all the details, in the top left corner, you start off with that data, and then you bring in industrial data from the NAICS system, you bring in spectral generators. We're going to do our disaggregation models, our flow models, PCEs, and we'll work our way down, and we'll do our traffic assignment. Now, when we get to the traffic assignment, we have access to artery flow data, GPS flow data, its average speeds by trucks on, well, currently 3-mile interval links, and I may get 1-mile interval links on the interstate. So we have some speed data, and we have truck count data from Georgia DOT site, a data site. So we can do some validation. And that's what most people do who do this right now. The only way they can validate the results of their model is, well, what extra data do we have on trucks? We have truck counts. Well, you may have, with 195-mile span of the interstate in this region, you have 4 sets of truck counts by truck class. So we're really struggling for good data, but most people, as they try to generate the trucks, have to go through all this industrial activity dollars to tons, to trucks, to PCEs, put it on the network, and it's a small miracle that you get the numbers that come out anywhere near those traffic counts. We tend to do. And for truck counts, it's not bad. If you're worried about easels and damage to the road, it's fine. But if you want to know what's actually on that truck and what the value of delay is, then you have to bring in the commodities. So that's what we're trying to do, and we'll end up with some performance measures. And Denise will probably do some energy and greenhouse gas emission calculations, because she's the green member of the group. Okay, so just quickly, the sort of things you do. Well, we've got zip code data. We bought some, we created a lot of data. This is just this Atlantis at the top right-hand corner. This is the corridor we're choosing at the bottom. And you can see a lot of the activity, as you would expect, is around the 3 metropolitan areas. But just how good is it? Well, our initial attempts to use equations which people have produced, either based upon employment, or based upon payroll, or based upon population, have not been very satisfactory. So with 40 commodities, 42 commodities, some commodities are not too bad. Other commodities are, when we apply them and we take a look at what we know about this area, they're not close. So we may have to have a mix of models. We may have to have some commodities generated based upon payroll. Oak Ridge did a very good job of looking at that, Oak Ridge National Lab. We may have to use some based upon employment numbers. Cambridge Systematics did some of those. The R-squares for these things, the regression models go from 0.1 to 0.9. It really varies. How do you deal with energy products? How do you deal with agricultural products? How the heck do you deal with wholesale? Which is just about everything you can think of pulled into one category. So we have a spatial and a temporal disaggregation, and we're going to take the literature and see which ones give us the best model, and then turn them into truck flows. Okay, so just we've been through the process once very briefly. So we fairly simple assumptions like 3 passenger car equivalents per truck, 20 tons per truck, type 8 and so forth, just to get it going, trying employment and what have you. So we're pulling out each of the different commodities. So Denise pulled out the truck flows between our states. And we don't know exactly which states. We know we're in the southeast, but we don't know exactly which counties are actually going to load onto our corridor. So we have to be more inclusive. So we generate flows, origin-destination flows, the 2 on the left, from and to, and then we break them down. That's just done by the FAC regions, by the way. Then we break them down into the 520-something, over 500 counties, and we load them into the system. We put them on the network, and you get this mess here. But it's actually not that bad a mess if we zoom in. And so that's one commodity, and we're trying to build it up for each commodities, and then figure out, and we're in here, our corridor is in here, there aren't many hogs and chickens going down there, maybe a couple of beef cattle. And that one is live animals and fish. After a while, you get so you can recognize the commodity, which is a little scary. But we can calculate those and build them up, and then get a sense of what's on the road. So our attempt finally in it is to what's the value of goods on the road that you're moving, and therefore, when we put it into the assignment model, and we already preloaded with all the freight analysis framework numbers on passenger flows. So we're preloaded it with passenger flows, and then we put, bit by bit, we build up the freight flows, including the local flows. So these are congestion-based. So when you get the estimate then of any origin-destination movement by a commodity type, you've got an idea of what the delay is. And the final model then is to how you calculate that delay for each of the commodities. And again, this is a lot of stuff here with lots of equations involved. But basically, we've got a vehicle type and a commodity type. They affect the fuel consumption. They affect the storage and handling costs. The assignment model gives us distances and travel times. That affects the labor cost. The truck costs are roughly a third labor, a third, well, it's changed a little bit more than a third. Fuel's the dominant one now, but fuel, labor, and O&M are the 3 real issues that you have. So we calculate those and end up with a handling cost. And one of the things we're trying to introduce into this is not just the average cost, the cost of an average trip, but we have travel time variability for every hour of every day in a year. So we can do standard deviations and other formulas on travel time, because the travel time variability is as important as the average time. Did a study a few years ago that people used one of the numbers, If you save, for every dollar that you save on a minute, time save, a minute save, you'll save $1.3 for reducing the standard deviation by a minute. A little complicated, but basically, standard deviation, on-time reliability is key. We're doing other studies on micro studies on automobile manufacturing groups for GDOT, and what we're being told is, boy, we can't afford to be down for an hour or 2 hours a day. It could cost us millions. So this is important stuff because it could be very high valued commodities, and what we're trying to figure out is how to get that value properly represented in a planning model. And the only thing I'm pretty sure of is we are underestimating the cost of congestion. Every highway engineer should be smiling broadly right now, because I think we can show that we're underestimating the value of reducing delay. Don't we get any money for it? We'll see. Anyway, that's it. We'll leave it at that. You get any questions?
Frank, you mentioned that you're doing ton-to-truck to PC conversions, and my research kind of goes towards that PCEs.
Yes.
I
wonder equations.
Where are you pulling, I mean, do you have an estimation equation for PCEs, or you just basically just...
No, we were using the standard PCEs, you know, you 2, 3, whatever we think, or whatever GDOT or one of the other DOTs
Okay,
things.
so as the tons...
It's a planning model, and you know, we have created an experimental design. We can have different disaggregations, we'll have different values of time, different PCEs, different truck configurations eventually. So we'll play around with it. But if you can give me an equation that I can plug in, that's fine. For an operational model, that would be the stuff you are doing.
Sure.
This is a planning model.
Okay.
And we're trying to say, what should you do in 15 to 20 years?
Okay.
Any other questions? We have a few more minutes.
Thanks, Frank. Okay, Bahareh Inaloo from UAB. Sorry, FIU, I'm sorry.
Good afternoon, everyone. I'm Bahareh, a PhD candidate at Florida International University. The title of my presentation is GIS-Based Routing of Hazardous Material Cargoes Considering Delay Cost after Accidental Release of Chemicals. Every day, more than 1 million hazardous material shipments is carried all over the U.S. And this societal cost of accidents involving hazardous materials through highways is more than $1 billion per year. The objectives of our study are health impact assessment of accidental release of gasoline, and prediction of probable outcomes, especially toxic vapor cloud, and finally routing the hazardous cargoes considering 2 criteria, health risk caused by toxic vapor inhalation and also delay cost. We assume a cargo track, a tanker track, carrying 6 full capacity, which is 9,000 gallons gasoline, have a crash, which makes it to lose its chemicals. The type of truck tanker is very common in carrying gasoline in the US, and we have also some atmospheric conditions as an assumption for this study. We also assumed an origin, which is Port Everglades in Hollywood, Florida, and a destination which is a gas station in Miami downtown. The reason we chose Port Everglades is that the port supplies 1/5 of Florida's energy and also provides petroleum products to 12 counties all over South Florida. As a methodology, we went through these steps. First, we specified possible routes for shipments, and then we calculated the health risk, and then delay costs, and afterward, which is the most important part of the research, is comparison of the routes based on these two criteria. The risk, which we calculated in this study, it comes through this equation, which is provided by DOT guideline, which is the multiplication of accident probability or frequency to accident consequences. To do that, we needed accident frequency was probability and accident consequences. To find the accident consequences, we use Aloha, which is an air dispersion model, able to calculate the concentration of chemical through the atmosphere. And this model sketches the impact radius and has this ability to export the outcome to arc map. So the outcome of the model comes through these shapes, which defining some levels of concern for health impact. We can have impact radius for a chemical which is released. So to have the consequence map, we define the cargoes and assume the cargo goes from origin to destination through a route, and then we sketched the impact radius of the chemical in case people inhale the chemical, and assuming that the cargo goes through the route and every person in the radius is basically at risk. So we sketched the impact area all over the route. And then based on that, we have the consequence map for each route. And based on the population density map, we calculated the population at risk for each route. In order to calculate the accident frequency, we use this very common equation, and using data, AADT for the network, and also the crash data for the whole network, we chose those crashes along the routes we selected before. So using those data and multiplying the consequent map to the crash rate, which is the frequency of accidents, we have the risk calculated. Now we're going to look at the delay cost calculation. We use queuing equation in order to find the delay time for the accident in case this accident happens. What is the delay time in order to convert it to cost? So we needed some data, AADT, route capacity, and capacity after accident. We found this data through highway capacity manual, and based on the route we selected, we chose capacity before accident and also some coefficients to calculate the residual capacity of the route. So based on this information, we calculated the delay time, and then multiplying the delay time to the cost for each hour, and each vehicle, we had the cost of delay for each route. So for different routes, the result came out to be like in this figure. As you can see, we have two criteria, delay cost and risk. As you can see, route number 3 has the most delay cost, but the least risk. However, route number 1 has the most risk and the least cost. At this point, since these results are in Pareto front solutions, we need the decision maker to give us its priority and its opinion of which of the criteria is more important for the decision maker, or for example, if the decision maker is priority of decision makers to have less delay cost, we may choose route number 1. Or even if the decision maker is willing to have an option to consider both criteria, he may choose route number 2. So we could efficiently predict the health risk and delay cost for different routes based on the data we have, and also because based on if we have the decision maker's priority, we can choose between those routes to choose the best possible route for carrying the cargo. For the future work, we're going to apply a multi-criteria decision-making method in order to compare the routes, every possible route, and then we figured that the crash rate and also the dispersion and dilution of chemical is different during night and day. So we can have our results comparing to those hours and have the schedule of cargo trucks. And also we can provide a network for an area to specify which segment is better to use for a cargo shipment. And also we can have a specific radius of public places to be avoided through the routes we are selecting for cargoes. Thank you very much, and I'm willing to thank Dr. Gan and Dr. Hadi for providing us data to get the research done. And the funding of this project was provided by Strive. Thank you.
Questions? We have time for questions.
One question I wanted to ask was, did you try other origin destination pairs, or was it just this particular OD pair?
Yes.
And also, this model seems to be a static model, I guess, in the sense that when you look at the dispersion of the chemical, are you considering time somehow? How fast it will disperse in a certain area?
Yes. About the origin and destination, the main focus of this study was to provide a framework for further studies. So we assume this origin and the other for destination. But depending on this destination and crash data, AADT, and every data we use, the outcome may differ, because this is all about the area, impacted area, and number of crashes through the route, and AADT. So if they multiply to each other, they may affect each other and have other data, other results. And about your second question, the model we use, Aloha, is a dispersion, a Gaussian dispersion model, which for this work, it looks at just 1 hour after the release. and looks at the concentration of chemical based on those levels of concern. For example, we want to look at this concentration, which above that we can expect people to have serious health issues or even death. So based on this concentration, after 1 hour of release, we did this research.
Another question is, in terms of, you identified 3 routes.
Yes.
Were there not any other routes, or you chose to only focus on those 3?
Yeah, we chose those 3 because we were looking to have the framework first and then apply other assumptions, and afterward finally have the network of segments which is proper for carrying the hazardous cargoes.
The reason I asked that was, it seemed like you are somehow trying to generate some kind of Pareto optimal frontier, I guess, based on the 2 measures you have.
Mhm.
Have risk versus the delay.
In this study, it was like it was not intentional, but as I said, based on the destination and origin and other data we have, these results may not be in Pareto front. For example, we may find a route which has the lowest cost and the lowest risk at the same time, and become very easily comparable to another result.
Thank you.
Danny Boston is next from Georgia Tech.
Thank you. I'm going to talk about the economic development and workforce impact of highway expenditures using Georgia Department of Transportation as a case study, but also looking at what are some of the national implications of it. So let me just kind of, before I go into the specifics, in this way allow me to get through the specifics in a much more efficient manner, let me just sort of back up and give an overview of what the project is. We've actually completed the project and it's gone through a review and it's actually being finalized now. But what the project is, what was the intent, and what are some of the major findings and implications, particularly from a policy standpoint. So we looked at all of the expenditures that on highways that were undertaken by Georgia Department of Transportation between 2009, January, and about April 2013. And we looked at each individual project expenditure. There were some 1,200 of them. And we also then mapped those individual expenditures to specific geographic locations. So the challenge, as you know, is to determine what is the overall economic impact of expenditures. And everybody looks at that all the time. You want to know how many jobs were created, what is the economic activity, how much tax revenue and other kinds of aspects were generated and other kinds of impacts. What we did differently in this study is that where in most studies where you look at that and you ask simply one broad question, how many jobs were created in the state as a result of highway expenditures? Or what was the economic impact? Or how much income was created? What we did was to actually disaggregate the data and go down to the county level. So there are 159 counties in Georgia. So we looked at that impact for each county. We looked at 6 different economic impacts at each county. Then we aggregated the county up to the 7 highway districts. So the state of Georgia is divided into 7 highway districts. And we looked at those impacts combined for each of those highway districts. And then we looked at it at the statewide level as a whole. Now, what was the importance of that? Well, the importance of it is that if you look at, for example, how many jobs were created per $1 million spent on highway projects, overall for the state, it's something like 16.6 jobs created per $1 million of expenditures on highway projects. But when you drill down to local areas, what you find is that that varies significantly by local areas, whether you're looking at how many jobs were created per dollar spent, or how much household income is created per dollar spent, or what is the overall economic impact. And there are a number of factors that influence that. For example, obviously the first thing is how much money was spent. But let's assume that the same amount of money was spent in each area, and GDOT did spread its expenditures across the states. There were multiple expenditures in each county. But then it also depends upon what industry what industry in which the industry in which the project was undertaken, right? So some industries are more capital intensive, others are more labor intensive. Well, that's kind of self-evident. But it also depends upon the geographic area where it takes place, because within that geographic area you have a certain supply chain characteristics. So prime contractors may be located there, they may be located outside of that area. They may use, for example, subcontractors. Those subcontractors may be within the area, they may be outside of the area. And then the final sort of degree of freedom it depends upon is what is the nature or the pattern in which individuals in that area spend their money. For example, do households generally buy products that are within the local economy, or do they buy products outside of the local economy? For example, if you look at Atlanta, and Atlanta Metro is in District 7, which is a sham lead district, and what you find is that they generate the lowest number of jobs per dollar spent of any district in the state, highway district in the state. And that's because we generally tend to spend, while we have a lot of money, we don't spend it all on products here. We spend on products from all over, right? Not just within the Atlanta metro area. On the other hand, if you look at the revenue that's going to small businesses in District 7, they have the highest amount of revenue generated per dollar spent. So those things vary, and it also varies even more when you drill down to the county level, so that it really matters. So if you want to maximize the economic development impact per dollar spent, then there are a number of factors that you have to take into consideration, right? Not just how much you're going to spend, but what is the makeup of the industry in the area, what's the characteristics of the regional economy, how many suppliers are in that area, right? And then how many prime contractors are in that area. And so those are the kinds of things that we looked at and ultimately came up with the conclusion that those are factors that need to be taken into consideration, because a dollar spent in, so for example, District 7 does not have the same impact as a dollar spent in District 1, okay? So then I can kind of run through this pretty quickly. So we look at the economic development impact, 2009 to 2013. We use the M-plan model, which is commonly used. It's the same model used to look at the impact of federal fiscal stimulus program. And we look at 6 categories. Output, we look at value added in production, new jobs created, how much household income is created, the amount of revenue that went to small businesses, and then also the amount of tax receipts generated in the local area. As I mentioned, it was unique because we drilled down to counties, and then we aggregated up to districts, and then finally to the statewide level. All right, so why is this important anyway? Well, we know that there's a very anemic job recovery in the economy, and everybody's talking about jobs, jobs, jobs. We need more jobs. The economy's been growing, although it's been growing, it's not been creating the amount of jobs. And the president in 2011 passed a memorandum that said they wanted to specifically focus on high job impact creation projects. So it's important to understand that, and it's also important from a national standpoint to understand what was the impact of the last Federal Fiscal Stimulus Act, so that if we run into another recession, does it matter that we allocate money towards infrastructure projects? And we looked at, for example, as a part of this project, we also looked at the amount of money that was spent in the Federal Fiscal Stimulus Program in Georgia and its impact. Georgia's job recovery has been among the slowest in the country, so it's important for Georgia to know that, right? How can we better allocate our resources? And also, the Department of Transportation wants to optimize scarce resources. So we're in an environment where there's not an abundance of resources, they're scarce. And so we want to make sure that we get the maximum output per dollar spent. And finally, stakeholders want to know more than ever, what is the impact of the amount of money that you're spending on my location? How much does it affect me? So those things are important. All right, so as I mentioned, Georgia spent between that period $3.1 billion on highway projects. That was spent on 1,271 projects. There were multiple expenditures in each one of the highway districts. The average expenditure was about $2.5 million. The median was just under $500,000. The largest cost of a highway project occurred in Chatham County. That's the largest total amount of expenditures, not single expenditure. Largest total amount of expenditures occurred in Chatham County. That's where Savannah is, 6.9% of all expenditures, followed by Fulton County. All right, but again, as I mentioned, there were multiple expenditures in all counties, and if you look at particularly on a district basis, they were spread fairly evenly across the districts. We also looked at what happened in the most recent year for which we had all data available, and then finally we broke down those expenditures. Also between the period 2009 and 11, the period in which the state received fiscal stimulus dollars in the amount of $604 million, and we analyzed the effects of the fiscal stimulus dollars. So what the report does, and you can't see these little numbers here, but it essentially drills down, and then for each one of these counties, we generated the amount of jobs that were created in each one of these counties, and then we aggregated the counties up to states and so on and so forth. So we want to know the total number of jobs and economic activity, and we did that for each one of the counties. We were able to estimate the local area impact, and then, of course, those impacts depended upon the characteristics of the local economy, the local supply chain, and household spending, all of which we examined. Again, we use the M-plan model, which the M-plan model, all it does is like it looks at sort of it's an accounting model that looks at how all 440 sectors of the economy are linked together, so that an expenditure in one sector has an impact on expenditure in another, and it ultimately produces multipliers, so that the multiplier tells you how much a dollar spent in this sector generates impact in another sector. There are direct effects, direct expenditure effects, indirect expenditure effects that come through supply chain reactions, and then induced effects that come as a result of income going to households and individuals in household spending. And these are all of the different impacts that we estimated, as I mentioned. Okay, summary of findings. All right, $3.1 billion led to a total combined impact of just under $6 billion. All right, for every dollar spent, there was a total economic impact of $1.90, right, per dollar. Spend $1, you get basically a $2 impact. Total number of jobs created was 51,000. For every $1 billion in highway expenditures, we created about 6.6 new jobs. All right, as I mentioned, the number of jobs created